Have you ever pulled a suitcase at an angle across the airport floor? Even though you're pulling in a diagonal direction, part of your effort goes horizontally to move it, while part lifts it slightly off the floor. That's resolution of vectors in real life. Hello learners! In today's session, we'll discover how any vector, say force or velocity, can be split or resolved into two parts along desired directions. This process helps us break complex, multidirectional vectors into simpler, one-directional components, usually along the x and y axis. This is especially helpful in situations involving inclined planes, projectile motion, or forces at angles. Let's understand how to resolve a vector along two non-parallel vectors in a plane. Imagine we have a vector A and we want to express it as a combination of two other vectors A and B which lie in the same plane but point in different directions. We draw lines from the tail of vector A parallel to vector A and from the head of A parallel to vector B. The intersection of these lines helps us form the equation A equals lambda into vector A plus nu into vector B. Here, lambda and nu are real numbers and the two component vectors lambda A and nu B together give us vector A. This generalized resolution approach is useful in systems where the axes are not perpendicular, such as oblique coordinate systems or tension problems involving pulleys. Now let's shift to the most commonly used system, Cartesian coordinates, where we resolve vectors along the x and y axis using unit vectors. Unit vectors are direction indicators with magnitude equal to 1. The standard ones are I cap along the x-axis, j cap along the y-axis, and k cap along the z-axis for 3D situations. A vector A in the xy plane can be written as A equals ax into I cap plus A into j cap. Here, ax and A are the scalar components of vector A in the x and y directions respectively. Using trigonometry, we find ax equals A into cosine theta and A equals A into sine theta, where theta is the angle vector A makes with the x-axis. We now have two ways to describe a vector completely. Option 1, by its magnitude A and the angle theta it makes with the x-axis. Option 2, by its component values ax and A. These two forms are interchangeable. If you know A and theta, use ax equals A into cosine theta, A equals A into sine theta. But if you are given ax and A instead, you can reverse engineer the vector using A equals square root of open bracket ax squared plus A squared close bracket and theta equals tan inverse of A by ax. This flexibility lets you move between polar and rectangular representations depending on what the problem demands. While we've mostly been in two dimensions, real-world physics often lives in 3D. That means breaking a vector into x, y, and z components. Say we have a vector A in space. Then its components are ax equals A into cosine alpha, A equals A into cosine beta, and as equals A into cosine gamma, where alpha, beta, and gamma are the angles made with the x, y, and z axis respectively. In unit vector form, this becomes A equals ax into I cap plus A into j cap plus A into k cap. To find the magnitude of vector A, we use A equals square root of open bracket ax squared plus A squared plus A squared close bracket. As you'll see in the 3D diagram, this allows full spatial representation of vectors such as those describing gravitational fields or magnetic forces. Let's now apply this concept with a practical problem. Imagine rain falling vertically at 35 meters per second and wind blowing horizontally from east to west at 12 meters per second. How should a person hold their umbrella? We treat the rain and wind velocities as perpendicular vectors Vertical vector VR equals 35 meters per second, horizontal vector VW equals 12 meters per second. Using the Pythagorean theorem, resultant are equals square root of open bracket 35 squared plus 12 squared close bracket, which gives are equals 37 meters per second. To find the angle of tilt, theta equals tan inverse of 12 by 35, which equals approximately 19 degrees. Conclusion: the person should tilt their umbrella 19 degrees east of the vertical to block the rain. Let's wrap this up. Why do we resolve vectors? Because it turns complex, angle vectors into manageable, one-directional components. This helps us apply Newton's laws, calculate motion, and solve for forces far more easily. Unit vectors I cap, j cap, and k cap give us a clear way to represent direction. A vector can be written as either a with angle theta or ax into I cap plus a into j cap. And with 3D resolution, we are ready to model motion in real space. So the next time you see a slanted force or an object moving diagonally, remember, behind it lies a clean pair of component vectors waiting to be analyzed. I hope this helped clarify how resolution of vectors works and why it's such an essential tool in physics. See you in the next topic, where we'll learn how to add vectors using their components.